Hi everyone. So in today's class, we are going to look at the boundary conditions. Alright, okay, we're going to look at the boundary conditions. Okay, so before we go to the boundary conditions, I think in this in this chapter, we have learned about two laws, am I right? We have learned about the Coulomb's law, and also the Gauss law. Okay, we have used them to find the electric field, right, of a point charge. Okay, so the electric field for a point charge can be calculated by this epsilon naught r squared and r. Okay, so when we're able to find the E, we're able to find the D. Okay, because the D is equals to epsilon naught. Okay, multiply with the electric field. And from the electric field also, we're able to find what is the force, right? Because the Q can multiply with the electric field in order to get the force. And if you observe all the formulations here, we have spacious parameters, okay, that you can define by using the calculator. That is the epsilon naught. Okay. So epsilon naught actually represent the dielectric. Okay, this one is represent the dielectric constants of the medium that the electric field propagate. Okay, the dielectric constant of the medium. So all the while we are using epsilon naught equals to 8.854 times 10 power negative 12. Okay, this one you can get it from your calculator. And this value is actually representing the dielectric constants of free space. Okay, sometimes, okay, the electric field, okay, they will propagate in another medium. Okay, so for different medium, they will have a difference of dielectric constants, and usually we use the relative permittivity, okay, or the dielectric constant to represent them. Okay, so the R represent the relative permittivity. So for free space, the epsilon R is equals to 1. Okay, so when you multiply with the epsilon naught, you will use this value for the calculations. But for the other medium, sometimes their epsilon R is not equals to 1. They can be equals to 2, they can equals to 3, 4, okay, whatever value. Okay, so when you want to calculate the electric field in this medium, you have to apply epsilon R multiply epsilon naught in order to get the permittivity of the medium. Okay, permittivity. Okay, of the medium. Okay, so we already know that this electric field can propagate in different mediums, okay, and it depends on the variable epsilon naught. We are going to use, in this section, we are going to use the boundary conditions to describe or find out the electric field, okay, in different mediums. Okay, boundary condition is what? Boundary conditions, okay, is the conditions that the electric field, okay, must satisfy, okay, at the interface separating the medium. Okay, so let us look at now this case. Imagine here, this is the interface between two mediums. Here is the free space, for example. Here, maybe is the water. So when the electric field, it propagates, okay, in the free space and going into the water, okay, the electric field will be different. Yeah? The electric field in the water will be different with the electric field in the free space. Okay, so we can use the boundary conditions. That is the conditions of the electric field at the boundary. Okay, this is the boundary that it must fulfill in order to find the relationship between this and also this one. Okay, so we are going to look at the boundary conditions, okay, at interface separating dielectric. Okay, that is when you have a dielectric, okay, and dielectric 1, and here you have another dielectric 2, meaning that these both dielectric, they are different. Okay, we will look at the changes of the electric field, okay, in these two different mediums, and we will also look at the boundary conditions, okay, at the interface that separate conductor. For example, it's a conductor separating with the dielectric, and conductor, okay, and free space. Okay, so before we look at the boundary condition for this interface, okay, there is one thing that you must remember is, okay, electric field, okay, can be decomposed. We can split the electric field into two orthogonal components. That is the tangential component T. The T stands for tangential. Okay, and normal component. This is something that you must remember at the beginning. N stands for the normal components. So let's see here. Okay, you have an electric field in the free space and in the water. You can always split them into the normal component. Okay, the blue one is the normal component, and then this one, okay, I will use the other colors, the green colors, okay, to represent the normal component. So this E in the water can be split into E tangential component, okay, in the water, and can also be split into the E normal component. Okay, so as well as for the electric field in free space, we can also split it into the tangential component, okay, tangential component, which is this one. Tangential components. Okay, tangential component. Okay, E tangential free space. Okay, and also normal component. Okay, normal component. E normal components with the free space. Okay, so you can split the electric field to two components over here. So this tangential and normal component, okay, they have an angles of 90 degrees. They are orthogonal to each other. You can see they are orthogonal to each other. Alright, so now let's look at the boundary conditions, okay, for dielectric and dielectric. Dielectric and dielectric. Okay, so you have a dielectric and dielectric. Boundary conditions. Okay, so I will draw a diagram. Okay, so this is the dielectric 1, and this is the dielectric 2. So this is a medium 1, and this is a medium 2. Okay, so this medium 1 has a relative permittivity equals to epsilon R1, and this one has a relative permittivity epsilon R2. Okay, so the first boundary conditions we can find out by performing a line integral of the electric field around a closed rectangular path. Okay, so now we are going to perform the line integrals, okay, of the electric field, okay, around a closed rectangular path. Okay, so it is a closed loop. So see here, I make a rectangular path, okay, at the interface between two mediums. Okay, so here I label it as A, and here I label it as B. We have a C, and we have a D. Okay, so the length over here, I will put it as delta L. This is the length. Okay, and then the length over here, okay, I would say that it is delta H over 2. Okay, this is delta H over 2. Now let's begin our line integral electric field in the closed loop. Okay, so the line integral of the electric field in the closed loop, okay, meaning that you have to do the line integrals one by one. Okay, so you have to integrate from line A to B. Okay, line A to B. Okay, and then from B to C. B to C. Okay, B to C. Okay, follow the locations. B to C. And then you have a C to D. C to D. And you have a D to A. Okay, they are in the closed loop. Clear? Okay, so the line integrals, okay, of the electric field in closed loop, you can split it into 4 sections. Okay, according to the sides of the rectangular path. Okay, so for the first one, AB, so it will be electric field. Okay, we look at the AB. Where is the AB? So now we are here. Let's move here. This is A, and this is B. Okay, so it will be equals to the electric field. Remember I said that the electric field, you can break it into the 2 components. Okay, you can break it into 2 components. That is the tangential components. Okay, tangential components, and also the normal components. Okay, so the electric field over here, okay, if you look at this line AB, and if you look at this line AB, it will be equals to electric field, okay, in the medium 2, right? This is medium 2. You can see electric field in the medium 2, and this electric field is the tangential electric field. Tangentials. Okay, dot product must be in the same directions, then only you will have values, right? If you remember. Okay, dot product, you must in the same directions, then only you will have a value. So this one will be the electric field, okay, tangential component multiplied with the length AB. So the length AB is delta L. Okay, plus Okay, BC. Okay, BC is over here. BC, right? So you are integrating it. Okay, you have to break it into 2 because you see this part belongs to medium 2 and this part belongs to medium 1. So it will be equals to electric field, okay, in the medium 2, and this is the normal component, okay, because it is in these directions, right? Normal components, okay, multiply with the length over 2, okay, and then plus the electric field, okay, in the medium 1 normal component, multiply with the length. Okay, so these two, okay, are for this term, okay, BC, yeah, BC, yeah, BC. Okay, next we move on to the DC. Sorry, CD. Okay, CD is over here, right? CD. Okay, so for this CD, it will be electric field, okay, in the medium number 1 and tangential components. Tangential component, medium 1 tangential, okay, multiply with the del L, the length, integrate. Okay, in this case, because you are integrate in these directions, right? Okay, you integrate in these directions. Okay, and these two directions, they are in opposite directions. So here you have to put negative. Okay, and for the DA, you see, DA is in opposite directions, okay, with the BC. Okay, so it will be negative also. So you have to break it into 2 as well. So it will be equals to E in the medium 1 and normal component multiply with delta H over 2. Okay, and minus E 2N multiply with the delta H over 2. Okay, so these two is representing this term. Okay, you have to minus because they are in the opposite directions with the previous one. Okay, so based on the conservative or natures of the electric field, you have learned before, right? Okay, in my previous lecture, I've talked about if you have to integrate the electric field in the closed loop, okay, it means that there will be no potential difference. Okay, it will be equals to 0. So meaning that this will be equals to 0. And this will be equals to 0. So if you simplify these two things, let's see what will happen. Simply, this is 2n, you see? You can cancel them. Okay, you can cancel them. See, this is E2n positive. This is E2n negative. You can cancel it. This is E1n positive. This is E1n negative. You can cancel it. So at the end, you only left this. Okay, which is E2n delta L minus E1t delta L is equals to 0. I will put like this, is equals to 0. And if you continue to simplify it, you can write it as E1t is equals to E2t. Okay, so you simplify this thing. Wait, wrong over here. This is 2t, yeah? It's 2t, yeah? 1t, 2t. Okay, so you can say that the tangential component in the medium 1 is the same as the tangential component of medium 2. Okay, so this is the first boundary conditions. Okay, and if you want to write in electric flux density, you could replace with d1t over epsilon 1 equals to d2t over epsilon 2. Okay, so here I want you to take note on this epsilon 1. So this epsilon 1 is equals to epsilon r1 multiply with the epsilon naught. Okay, and for this one also, okay, it is equals to epsilon r2 multiply with the epsilon naught. So we have produced the first boundary conditions, and later on I will show you how to use these boundary conditions. Okay, so this is the first one. So we have defined the first boundary condition. Next, we are going to find the second boundary conditions by using the Gauss law. Just now is the first one, now is the second one. I'm using the Gauss law. So I hope when I mention the Gauss law, the equation will automatically appear in your mind. Gauss law. So the Gauss law says that the total flux coming out from the surface is equal to the Q that is enclosed by the surface. Okay, now let's apply this law in the interface, okay, that has two mediums. Okay, so this one will use back the same mediums. So we have medium 1 and medium 2. So we have medium 1, epsilon r1, and we have a medium 2, epsilon r2. Okay, so in Gauss law, we focus on the parameter D, right? That is the electric flux density. So just now we focus on the electric field. Okay, we know the relationship between the electric field and also the electric flux density. When the electric field can be split into the normal component and also the tangential component, so this electric flux density can also be split into normal component and also tangential components. Okay, meaning that, okay, if you have this thing, this is the electric field in the medium 1, okay, you can split it into normal components and also the tangential components. Whereas for the medium 2, okay, if this is your electric field, okay, you can also split it into tangential components and also normal components. Okay, so in this case, we are not using the E, but we use the D. So the D can be split into normal components and tangential components. Okay, they have directions. So here I will label it as, this is a D1. I will label it as D1 normal. And this is a D1 tangentials. And this is a D2, right? So you have a D2 tangentials. And this is a D2 normal components. You split into two. Okay, so in order to find the flux, okay, in the mediums, find the D in the mediums, okay, we construct a cylinder. We construct a cylinder. Okay, so now I construct a cylinder. Okay, this is a cylinder. Okay, so the flux coming out, okay, from the surface of the cylinders, you can have a flux here, right? Okay, so this one is following the D, the D1N, okay, and this one is a D2N. So this is the flux coming out from the surface, from the top and bottom of the cylinder. Okay, and if you assume that, okay, the del H over 2 here, okay, del H over 2 is over here, and the del H is approximate to 0. Okay, when the del H is approximate to 0, then we said that there is no flux, no D, okay, from the side surface. Because the H, the del H, the height is too small. So there is no flux coming out from the side. Okay, so now we apply the Gauss law. Okay, so the flux coming out from the surface will be equal to the Q enclosed by the surface. Right, so now the surface we'll consider is the top surface and also the bottom surface. We won't consider the side because the del H is very small. And in this case, okay, the Q, okay, we will use this Q equals to rho S ds. Rho S ds. In case if we have this rho S on the at the interface over here, imagine if we have a charge at the interface. Okay, so this one will be the rho x. Okay, so this one we can write it as the rho x multiplied with the del S. Del S is the area, we just represent it with del S. Okay, so for the top and bottom, okay, it will be equals to the, if we look at top, okay, the top will be equals to D1N multiplied with the area, right? Area of the top. And for the bottom, okay, for the bottom, it will be negative. Okay, why negative? Okay, if you remember this one, we have to look at the directions of the surface, right? So in this case, for the top surface, your D is upward, and also the surface is facing upward. Okay, same directions. Okay, same directions. This one is your surface. Okay, the surface directions. The surface directions is upward. And at the bottom, the surface directions is downward. The surface directions downward. That's why this make this part, okay, to be negative for the bottom. So you have bottom negative. D2N. D2N. I think this one should put here. Okay. D2N multiply with the del X equals to rho S del S. Okay, so if you simplify this relationship, you can say that the D1N minus the D2N is equals to rho X. Okay, so this one, you will apply it when there is a surface charge, okay, at the boundary between two mediums. Okay, but if the surface charge is equals to 0, if the rho X is equals to 0, then the D1N will be equals to D2N. Okay, so we get the second boundary conditions equations. Okay, D1N equals to D2N. If you want to rewrite it, okay, using the electric field, so it could be D epsilon 1 electric field 1N equals to epsilon 2 electric field 2N. Okay? So E1n equals to E2n. This is our second boundary conditions. This is our second boundary conditions. This is the second boundary conditions. Just now we have the first one, so this is the first boundary conditions. Later I will show you how to apply, okay, these boundary conditions. Alright, so we'll now look at the reflections, the reflection of the electric field across the interface. Okay, the refractions of the electric field. Of the electric field. So let me draw again the interface. This is the interface of two mediums. You have a epsilon 1 and you have a epsilon 2, and you have the electric field, okay, in the medium 1, okay, and you have the electric field, okay, in medium 2, for example. And you can break it into two components, like we mentioned earlier. There is a normal components, and this is the tangential components. So this is a E1 normal, E1 tangentials, and this one also you can break. This is the E2 normal, and this is the E2 tangential. Again, you can break into two. So you can see here actually you will have angles. Okay, angle 1, and if we extend this line, we could have angle 2. So the electric field is like refracted. So let's find the relationship between the angle 1 and angle 2 with the properties, okay, with respect to the properties of the mediums, the relationship. Okay, right, so we use the first boundary conditions that we have, that is E1t equals to E2t. This is the first boundary conditions. Okay, so we see that 1t is over here, right? 2t is over here. Okay, we could rewrite both of them with E1 multiply with the sine theta 1. Okay, so this is the relationship, right? Sine theta 1. Okay, so where is E1? E1 is over here. Okay, E1t. E1t is over here. You can actually move this E1t over here. Oops. E1t here. Right. I know this is the E1t, but tangential component you can also write it here. Tangential component, as long as it is tangentials, okay, you can either put it here or you can either put it here. Okay, doesn't matter. Okay, so the E1t, okay, for you to imagine, I will put it up there. So you can see a triangle, right? You can see a triangle. And this is the angle theta 1. And this is the E1, right? And this is the E1n, and this is the E1t. Okay, so if you want to find the E1t, okay, we can use the sine. Okay, that is the sine theta 1 is equals to opposite over hypotenuse. Okay, so it is E1t over E1. Okay, so when you want to replace the E1t, okay, you can multiply the E1 with the sine theta 1. Okay, that's why you get these equations. And for the E2t, we can use similar way to do it. That will be the E2 multiply with the sine theta 2. Okay, so this is the first equation that we get. Okay, now we go to the second boundary conditions. So the second boundary condition is D1n is equals to D2n. Okay, so the D1n, where is D? This one we can write it as the E, or we can write it as a D also, right? We can also write it as a D. Okay, so this is the D1t, and this is the D1n. Okay, so for the D1n, okay, the D1n is over here, the D1n. Okay, you can define the D1n as D1, okay, multiply with the cos theta 1. Okay, where is D1? D1 is here. Okay, this is D1. And this is the D2. Okay, and D2n could be equals to D2 cos theta 2. Right, so if you replace the D with the epsilon, so it will become epsilon 1 E1 cos theta 1 equals to epsilon 2 E2 cos theta 2. Okay, so now let's divide the first equations by the second equations. And this is the second. Okay, so what we will get? So we can put this one as a divide. Okay, we simplify. We try to simplify it. And for this sine theta 1, cos theta 1, you can replace it with tangent theta 1. And for this part, you can replace with tangent theta 2. Okay, so the whole thing will become tangent theta 1 over epsilon 1 equals to tangent theta 2 over epsilon 2. Okay, so if you slightly adjust a bit their positions, rearrange it, tangent theta 2, epsilon 1, and epsilon 2. So we know that the epsilon 1 is equals to epsilon R1, epsilon naught, okay, epsilon R2, epsilon naught. Okay, so we can cancel the epsilon naught. Okay, we can cancel this thing. Right, so now this will be the relationship between the angles and the dielectric constants of the medium. And they are derived by using the boundary conditions, okay, that we have derived earlier. Okay, so this is the relationships. Okay, so now we are just looking at the boundary conditions between the dielectric and dielectric. What happens if one of the dielectric is replaced by conductor? Okay, so we look at the conductor and dielectric boundary conditions. Okay, so this means that, okay, now you have a medium one, it is dielectric. Okay, epsilon 1. Okay, and your medium 2 is a conductor. Conductor that conduct the electric currents. Okay, so what will happen to their boundary conditions? So in fact, the process to derive the boundary condition is exactly the same like the previous one. But here, okay, there is something that you must remember is there will be no electric field in the mediums of conductor. Okay, no electric field. No matter in what conditions, there is no electric field in a conductor. Okay, so when there is no electric field in the conductor, it means what? It means the E2N is equal to 0. And the E2 tangential is also equals to 0. So when this happens, if you take out the boundary conditions that you have derived earlier, okay, this is 2t, okay, we have derived this one, right? If the 2t is 0, so the E1t is also 0. And let's look at the electric flux density. E1n equals to D2n. E1n equals to D2n. When the normal component is 0, and this is also 0, so meaning that the D1n is also 0. E1n is also 0. Okay, means that is totally no electric field. Okay, however, if there is a surface charge, alright, this is a special case. If there is a surface charge over here, rho x, okay, this one will be equals to D1n minus D2n equals to rho x. Okay, your D2n equals to 0. Okay, so your D1n will be equals to rho x. Okay, so this is something you have to take note. No electric field in the conductors. Okay, when there is no electric field in the conductors, okay, means that there is also no potential difference between any 2 points in the conductor. For example, just imagine this is a 2 point inside the conductors. There will be no potential difference. The VAB is equals to 0. Or maybe you can imagine like this. You take a conductor and you put the probe of your multimeters at 2 points of a conductor. One, you put it here in the B. Oops. One you put it here, the probe of the multimeter. The other you put it here. Okay, you can track the reading of a multimeter. The reading will be 0. Okay, so showing that there is no potential difference in the conductor. Okay, and the conductor is an equipotential body because they are equipotentials. EQUIP, potential. Equipotential means the potential is the same everywhere. Okay, it's the same everywhere. Right, so this one is happen when the boundary is conductor and the dielectric. Okay, You can also have a boundary that is the free space, and dielectric. Boundary conditions. Okay, so this one is quite similar to the first case, dielectric to dielectric. So this is a dielectric. Okay, and this is the free space. So dielectric, you will have epsilon r, and for the free space, the epsilon r is equals to 1. This is just difference. Okay, so when you apply the boundary conditions, you can apply as usual. You can apply as usual. Okay, use this one and this. Okay, oops. As long as you replace the value of the dielectric constant properly. Just apply like usual. Okay, but if the dielectric is, for example, this one replaced with conductor, then the answer will be the same like this, the second case. Okay, so I think you don't need to memorize all the boundary conditions. Okay, no matter it is free space and dielectric or dielectric with conductor, you don't care. Okay, you just make sure that you remember the first boundary conditions and the second boundary conditions and the relationship between the D and also the E. Okay, so basically you can apply. Okay, you can apply it in all cases. So just now we mentioned that the electric field in the conductor is equals to 0. This is a thing. Because of this characteristic, we always use the conductor as a shielding material. For example, now you have sensitive devices. This is a sensitive devices. Okay, sensitive electronic devices. Okay, and here there is also another, for example, there is an antenna, TV antenna. Okay, this is antenna. So this antenna intends to radiate the electric fields. Intends to radiate the electric field in all directions. And this sensitive device, when it is exposed to the radiation from the antenna, okay, it cannot function properly. Cannot function anymore. Cannot function properly. In order to avoid, okay, and protect these sensitive devices, we can shield it by using a conductor. Okay, you can shield it by using a conductor. Okay, so when we shield it by using a conductor, okay, meaning that the electric field radiated by this radiator or antenna, it cannot go through. It cannot go through the shielding conductor. Why? Because the electric field in the conductor is equals to 0. No matter how much is your electric field over here, it cannot penetrate, okay, to the electric field. It cannot penetrate the conductor, okay, because the electric field, okay, in the conductor is equals to 0. So as a result, okay, this sensitive device can operate safely without being interfered by the antenna. Okay, so this one is a shielding. Okay, shielding properties. Why the conductors, electric field in the conductors is equals to 0? I think I explained before in my video, right? Okay, so when you have let me see, where is the slide? Okay, so this is a conductor. I think I explained in the video. This is the conductors. Okay, when the conductor is exposed to external electric field, you see external electric field, external electric field. Okay, so this is the directions of the electric field. Okay, so all the positive charge, they will align at these positions. Negative charge will be aligned at the other positions. So internally, there will be electric field in the opposite directions. okay, as the external electric field. So these two directions that cancel this internal electric field, they cancel the external electric field. This is external, this is internal. Okay, so as the result, okay, there is the E is equals to 0. Okay, you can bring back the video I explained before. Okay,